corresponding means let us represent EL, EMF induced because of phi L, and this EL will oppose the cause. This is effect of phi L and cause of phi L is E. Because of E, once load is connected, armature current is flowing. Because of armature current, armature flux is there, and armature flux is having two components, one phi L and another which is contributing to the useful flux, right. So this will oppose its cause, that is E. Hence, while writing EL, and this will be proportional to armature current, so EL may be written as equal to IA times one constant, and that constant of proportionality will be nothing but XL. Sign we will take care of later, JXL or like that, plus minus, it is opposing, hence minus like that, right. So we may write direct axis synchronous reactance as XAD, this hypothetical component, plus this leakage reactance. Mark equation 1 or A. Similarly, quadrature axis synchronous reactance may be marked as XAQ plus this XL. Because this XL will be everywhere along D axis, Q axis, wherever, right, we have distributed windings on a stator. So mark it B. This XL is determined by Poisson triangle method. We will study in upcoming lectures Poisson triangle method. By performing zero power factor test. We will study in detail. So this XL may be obtained by performing zero power factor test by means of Poisson triangle method. These two, XD and XQ, will be determined by using slip test. We will study in our upcoming lecture what is slip test. So by performing these two tests, zero power factor test and then forming Poisson triangle and then obtaining XL and slip test, now we know XD, XQ, XL and XL, right. Then we can easily evaluate these two hypothetical components XAD and XAQ assumed by Doherty and Nickel in order to obtain, study the effect of armature reaction for various power factor angles. Fine. So if we are going to summarize the things, then we have, if we are going to draw per phase basis, then we have EMF induced E, EMF induced E, then one more drop, and that drop will be represented by, if we are representing current as IA, here IA, this is E. What is IA? Armature current flowing in armature winding. So we may write here JXAR. So this will give armature reaction drop. IA XAR will give armature reaction drop. So the resultant of these two will be another EMF, not exactly the internal EMF but different than that. If IA is not flowing, so this drop will be 0, it means IA is absent, that is load is not connected, it means no armature reaction effect. So whatever the EMF, internal EMF is induced, the same will be available here. So just write ER, resultant. ER. So, if current is flowing, armature reaction is there. So, whether demagnetizing or magnetizing depending upon whether IA is lagging or leading, depending upon the type nature of load connected to the alternator, we will have some drop corresponding to armature reaction drop. Then we have this leakage reactance drop which will oppose. So, just represent it by JXL. So, that drop will be decreased from this drop. Once current is flowing, these drops will be there. When current is not flowing, this drop will be 0, 0 into something 0, 0 into something 0. And our windings are having some finite resistance. So, once current is flowing, some resistive drop will also be there. So, just write here one resistance, represent it by RA, and then whatever EMF is obtained, that is, let us represent VT or V like that, terminal voltage. So, this will be the terminal voltage available at the terminals. If load is not connected, all these drops will be 0, IARA drop will be 0, this drop will be 0, this drop will be 0. So, whatever internal EMF induced is there, the same EMF is available at the terminals. But once load is connected, so depending upon the nature of load, these drops will be different and also amount of load current, right. So, this terminal voltage will be different than the internal induced EMF. So, the power factor angle, that is angle between IA and internal EMF induced, is represented by psi, and this is known as internal power factor angle, whereas the power factor angle between the same I armature current and terminal voltage is known as, represented by generally phi and known as power factor angle, simply power factor angle, load power factor angle. So, I think you can easily distinguish between these two power factor angles, internal power factor angle, angle between internal induced EMF or excitation EMF and armature current, whereas this power factor angle is not between E and I, but between VT and IA. Fine. As we discussed that VT will be different than this once alternator is loaded. So, in case of cylindrical rotor machine, these two XD and XQ will be equal. XD will be equal to XQ for cylindrical rotor machine, whereas XD will be greater than XQ for salient pole machine. So, generally this XD is, this XD right here, this XD is XAD or XD, right here XD, okay, we may write XD is greater than XQ for salient pole machine. So, this difference XD minus XQ is known as saliency of machine. Generally, XD is taken as 1.6 times XQ. Generally, it may be up to twice or like that, double of that for salient pole machine. But for cylindrical, XD will be equal to XQ. So, XD minus XQ for this will be 0, that is saliency is 0, it means it is not salient pole, it is non-salient pole. That is why the name for cylindrical machine is given as non-salient pole also, because its saliency is 0. So, for cylindrical we may represent it by XS. Remember that XD is nothing but XAD plus XL, XAQ plus XL, XQ is XAQ plus XL, and this is XS. This RA, armature resistance, plus this XS, synchronous reactance, is together known as synchronous impedance, that is ZS may be represented as RA plus J XS. Fine. So, these things will be discussed in detail while discussing the phasor diagrams for each and every type of machine for various power factors in our upcoming lectures. So, this is all about for today's lecture. Thank you very much.